Continue, okay. So today, let's see, make sure I record it, okay. Okay, good, it's recorded. So today we move on chapter 5, okay, continuous distribution. So in chapter 4, we learn the discrete distribution, right? So where discrete distribution is used to study the discrete random variable, right? Which is random variable with discrete outcome. Say, number of people call you today, right? 1, 2, 3, 0, 9, 6, I don't know. Number email your inbox, right? It's a discrete thing, right? A number of heads when you toss a coin 10 times, right? It's all discrete. So this was solved in chapter 4, right? So in chapter 4, what did we learn was we learned how to make a table, right? To represent the discrete random variable, the distribution of the discrete random variable, where in one column you have the value, and another column you have the corresponding probability, okay? And you also use another tool where we use the binomial distribution, right? To model in the case, say you have a large scale outcome, right? Because for a table, say, you can make a table with 10 outcome and 20 outcome, that's okay, right? But say if you have maybe 1,000 outcome, right? So say you toss a die 1,000 times and you keep track number 6, right? Another time, for sure, you don't, the table won't be a good tool for you to study, right? Another time you need a distribution. And in chapter 4, we learned the first type distribution is the binomial, right? One type distribution, right? You have more distribution beside the binomial, but because for this scale, this class, we just introduce for you a little bit of everything, okay? Kind of you have a place for helping go with this. And this is why this class is going in a fast pace, okay? Some you suggest, can we go more example, do 3 or 4 example for one new concept, but it won't work for this class, okay? Because that thing you do with your homework, okay? And because, if we do that, you can never finish 10 chapters in one semester, okay? There's no way, okay? But 10 chapters here in the 400 level, we need to break down in 3 different classes, to make it in the depth level. But for you, because you want to introduce everything to you, so this way it has to be fast paced, okay? So this chapter, we don't learn discrete, but we learn continuous, okay? Continuous. Which we learn the distribution, okay? Continuous distribution, which is used to model the random variable with continuous outcome, right? So we need to look at chapter 2, right? So continuous random variable, basically say, the high people, right? Some people 5, 5, 1, 5, 2, 5, 2, 1, 5, 2, 2, right? Say, the weight of newborn baby, right? 7 pounds, 7.1, 7.01, and something like that, right? And maybe the full range, the range of an electric car can run, right? Can drive after a full charge, right? It can be 300 miles, 301, 301.11, something like that, right? It's all continuous random variable. And to study the continuous random variable, you need a different tool, right? Compared to chapter 4, right? We need something called continuous distribution, okay? So this is the goal for today. We start to look at the continuous distribution where it's used to study continuous random variable, okay? So first thing first, there's some terminology. The first terminology called continuous random variable. So this is this terminology you already see in chapter 2, right? Which is a random variable with continuous outcome, right? Continuous outcomes, right? The height of the random chosen person in the US, right? Weight of a newborn baby in Atlanta today, something like that, right? It's all continuous random variable. In order to learn about that, right? Continuous random variable, you need a tool called continuous distribution, right? Distribution. And that's used to model the distribution of continuous random variable, okay? And when you model, you want to learn the continuous random variable, for sure, you want to know the probability, right? Of where we have more observation, where we have less, right? So in the slide here, we have 3 different cases for 3 different continuous random variable, okay? So the first case here, basically like we have a random variable where the outcome from 0 to say infinity here, okay, on the left side, okay, left side. And at that time, the probability of the random variable you get observation, okay, between a certain belong to certain area can be looked at by the area under the curve, okay, area under the curve. So for example, in the first plot here, on the left hand side here, the shaded area here, it tells you, okay, what the probability you can get an observation between A and B, okay. So for example, hey, here we say A5, B6, okay, and we use this random variable. This is a curve here, okay, to model the high people in the US, okay. So say what probably a person in the US, okay, randomly chosen person, their height between 5 and 6 feet, right? 6 feet here, okay. So the area under the curve here, it tells you what the probability is, okay, of that height, okay. And for sure, for this curve, you can also see that you have the observation is center around the area close to A, right? And you have more, you should expect less observation from the area after B, right? You have less observation. So most of the observation, when you collect the data, it should be around the peak here, okay? The most here, close to A here. And if you look at the middle figure, right, which is in this case, I think the blue or purple here, it also tells you what the probability of your observation between 40 and 60 is. And so if you randomly choose a person, say, or whatever this model do, okay, and one probably between 0, 40 and 60 in the area under the curve, okay. And again, the same thing here, okay, the pink one here for the the third figure here, okay, it also show you the probability of you get observation from between C and D, okay, C, D, okay. So now you see we have different way to represent probability, okay. Now the probability is represented by the area under a curve, okay, area under the curve. Different, okay, it's different with what you saw before, right? And then basically like now to find the probability, your job become finding the area under the curve, okay. We have tool to find that too. So this is basically like it comes back to the geometry type problem where you learn in your 4th grade, 5th grade, 6th, 7th grade, right? So have you ever wondered why we need to learn geometry? Right? Isn't it fun? It's fun, but eventually they build up to make these things, okay? To make these things, okay? So often, when you're in high school, right? You ask why we need to learn math, right? So now you start to see math need to be learned in high school to, eventually to build up these things and for engineer and for different things, okay? For different purpose. Okay. So now we have another terminology called probability density function, okay? Sometimes we call it density curve, okay? So which is a curve, it represents, how the random variable is distributed, okay? So for example, in this curve here, right, you have on the top here, right, you have a density curve here. In this case, it's kind of a normal curve here, okay? A normal curve. And basically like if a random variable, a continuous random variable, you can specify the density curve, okay? If you can specify what is the density curve, and other time, basically like mathematicians, statisticians, they can help you to know everything about the distribution, okay? What is the mean? What is the standard deviation? What is the probability, you get an observation belong to a certain area, okay? A certain area, okay? So this is the first concept for the density curve, okay? So now you need to know that for each continuous random variable, it will tie with a probability density curve, okay? We will tie with a density curve probability density function, okay? It will have a uniquely determined by probability density function, okay? And then another concept called a cumulative distribution function. So this thing is also familiar with you, which is CDF, right? When you look at the binomial distribution. So basically it's just like the probability of your random variable, you observe a value less than or equal to certain value x, okay, x, okay. So at the time it's called fx, okay. So for example, in this case, if you look at the curve here, the CDF, which is the shaded area here. So everything less than x, right? So basically like the shaded region, okay. So the top, the plot at the top, okay, at the top. So it tells you what is the fx or the CDF of x. Okay, so sometimes you write CDF x, sometimes we write fx. Okay, but most of the time people will write fx. Okay, capital Fx. So which means the probability your random variable less than equal to x. Okay, less than equal to x. So in this case, like the shaded area, basically it's just a f1. Okay, it's just f1. So in this case, the shaded area here is just a f1. Okay, f1, right? A probability of x less than equal to 1. Okay, less than equal to 1. And then another thing is that this is the most important thing, right? We care about. What is the probability of your random variable between a certain range, A and B, okay? So other time, it will be the area under the density curve here, okay? So it will be the shaded area here in the brown color here, right? So if your density curve, okay, and then the probability you observe a value between A and B will be the shaded area here, okay, the brown area here. If you look at the bottom plot, okay, bottom plot here, okay. So just probably A X between A and B, okay. So think, if you model, right, again, hide a few people, right, by this density curve, right, and then maybe make it specific, A equal 5, B equal 6, right? So probably you can, a randomly chosen person, his or her height between 5 to 6 will be the error under the curve here, error under the curve here, okay. The shaded, the brownish error again. Okay, so let's look at one example. Okay, so you can see how this thing can be used. Okay, so suppose the waiting time at the bus station, okay, is uniformly distributed between 0 and 20 minutes. Okay, so you go to the bus station, the waiting time, according to the empirical data, I see that it can be anything between 0 and 20. Okay, so it can be 0 minutes. You come see the bus, you will hop on and go, right? You maybe wait 1 minute, 2 minutes, but it can be, you say, if you will have very accurate watch, right? So it can be 1.1 minutes, 1.01 minutes, right? It can be anything between 0 and 20, okay? So if you didn't know X the waiting time, okay? So X will be a continuous random variable, right? It's X continuous random variable. The other time, the probability density curve, okay, it can be shown that, okay, for this curve, okay, the density curve, it can show that it will be have this value, okay, 1/20, which is 0.005, okay, 0.005 here, okay. So the density curve, just the blue line, okay, the blue line you see in the first plot here, okay, it's just everything fixed is 0.005 from 0 to 20, okay, from 0 to 20. And actually, we can also show that, okay, eventually we have that property. The other time, if this is the PDF, okay, and we can also show that the CDF are the cumulative density, okay, the probability of X less than a given of the value of X, small x here, will be equal to X by 20, okay, X by 20. It's also easily can be shown, okay, can be proved, okay. But here we just add this step, we just set as a fact, okay, to demonstrate, if you have a continuous random variable, and you decide to model by something we call uniform here, it will have a certain PDF, right? Which is probably density curve, and in this case, it be like 0.05 for everything from 0 to 20, and CDF, which is a cumulative distribution function, is actually by 20. Okay. So with the CDF, one application you can see right away is that you can find what F10, right? So F10 basically like probably X less than equal 10, right? Which means the waiting time less than 10 minutes, right? And if you plug in this function, you see that it will be 10 divided by 20, which is 0.5, right? So while probably I go to the bus station and my waiting time less than 10 minutes, right? Less than equal 10 minutes. So other time it's just 0.5. And you can add the same thing, right? While probably I go to bus station and my waiting time less than 5 minutes, right? So it's just 5/20, which is 0.25. While probably my waiting time less than 15 minutes, right? Other time will be 15 by 20, you have like 0.75. So you can get everything from that, okay? And also for this case, right, F10, which is the error under the curve here. So everything up to 10 minutes, right? And for sure, you can see that, it will be 0.5 if you do some geometry calculation, okay? Here just 10 and this, you get 0.5, okay? 5. So let's look at how it's related to discrete distribution, right? So previously, we get the discrete distribution, right? So here an unfair dice, okay, with the probably yielding 6.6, okay. So if we have that unfair die, okay, and we didn't know x is number 6 in 20 toss, right? And for sure, x will be binom 20 and 0.6, right? Because now you have unfair die, okay, and with probably yielding 6 is 0.6. So if you consider x is total number of 6 in 20 toss, and then you can model by that, right? And basically, if you can model your binomial with discrete distribution here, and two ways you can represent the probability. One way is that using the table, right? So all the value, number of 6 turn out can be 0, 1, 2, 3, 4, 5, up to 20, right? And each value, you have a corresponding probability, right? Corresponding probability. And from that spirit, right, you can also visualize that by building something we call scatter plot here. So you put like each dot here will be represented for the outcome and the corresponding probability. So for example, you have like you look at the dot at the 9, right? At 9. So you see like here like the height of that dot, it tells you the probability of we get 9 number 6, right? 9. In 20 toss you get 9 6, right? So at that time you get about point something here. I think 0.1, okay, 0.1, about 0.1. 9, yeah. Okay. And also you can get like what probably you get like 12, 6 or something like that, right? You can also get those things by the height. Look at the height, right? But so this for discrete case, right? So you can see it chart, right? Chart here 0, 1, 2, 3, and you see the point here chart here 0, 1, 2, 3, 4, 5, right? But for continuous, it's different story, right? Continuous did not chop anymore. It had to be smooth. Okay, it had to be smooth. Because absorption can be any, okay, can be anything in the range of the random variables. So because of that, so basically here's some property, okay? You need to know when you work with the continuous distribution. One important property, and it makes it different with discrete random variable, is that probability of x, okay, your random variable x, okay, equal to a certain point, a, okay, for any a, okay, it's always 0, okay, it's always 0. So very different with discrete random variable, okay. So the weight at any point must be 0, okay, it must be 0, it must be 0. So this is a very different discrete random variable, right? So you can see for discrete random variable, you have here maybe, for example, like probably you get like 26, right? X equal 20, you get like 3.656 times 10 negative 7, right? You get something in the middle here, right? Probably x equal 12, whatever here, right? You can get those things. But for continuous, okay, it's over 0, okay? And there are mathematical reason behind that. So basically, you can think that, you know, if you assign any weight, maybe say 0.001 for a 0.8, right? But you should remember for continuous random variable, you have infinite many outcomes, okay? Billion outcomes. So if you assign even a very small weight, say 0.01, so for 1 point, right? And you have, because you have infinite many outcomes, so you say if you have 0.01 with infinite outcome, you get infinite. Okay, so which means the total probability now it becomes infinite number, and if you violate the requirement for definition of probability, right? The probability must be between 0 and 1. It cannot bigger than 1. Okay, so basically the mathematical reason behind that is because the infinite outcome. Okay. And given that, so you can see that when you work with continuous random variable, a nice thing for you is that you don't need to look at the equal sign. You can use the equal sign, you can drop it. It won't affect. It will be different with the discrete case, right? So discrete case, if you look at the test 3, right? Probably you get a less than 4, right? So less than 4, which means your calculator cannot do that. So you need to translate to less than equal 3, right? Less than equal 3. And from that, yeah, I can do that for you. But for continuous random variable, you don't need to look at it, okay? Less than 4 or less than equal than 4, the same. You don't need to look at the equal sign, okay? So which means you can get, let's see, probably x less than equal b equal probably x less than b, and it's also the same as fb, right? fb. So which means that the equal sign not matter, okay? Not matter, okay? You can drop it or you can keep it. It won't affect your result, okay? And here are some small different property here, okay? Another property where, say basically like property x between a and b, okay? Can also translate it by this fashion, okay? Which is probably x less than equal b, subtract less than x less than equal a. We see this type of can already in binomial distribution. But here you see again with continuous scale, right? So you can see like x from a and b, which is this area, right? Will be equal to the shaded area here, everything up to b, right? And subtract everything up to a. So basically, if you do that two subtraction part, you get the remaining, which is from a to b, okay? And equal fb subtract fa, right? This is the definition of the cumulative distribution function. Fb is equal to probably x less than equal b. Fa is equal to probably x equal a, less than equal a, okay? And the last property also very important is that property on the whole sample space, right? Must be one, right? So say if your x can take values on the interval range from c to d, right? Then probably x between c and d will be one, okay? Must be one. Probably cannot be bigger than one, okay? Remember again. Probably must be number between 0 and 1. 0, which means the impossible event. 1 means the surely event, right? Like the sunrise tomorrow, right? Impossible event, like yeah, that's right. People will live in the sun, right? Okay. Yeah. So say again, so say for example, then maybe you look at like the high people, right? The high US people. So if you believe that the heights can be modeled by 0 feet to 10 feet, right? 10 feet, right? A person, we never see have any person like 10 feet tall, right? The tallest one, 8 something, when you look at Google before. So maybe at other time, say if you model by 0 to 10, so you can see that for a random chosen person, the probability he or she, his height between 0 to 10 is 1. It must be in that. It cannot be more than that, right? So here is some common continuous distribution. Okay, so in this class, we look at the number 1, number 3, which is uniform and normal. Okay, number 2, the cost coordinator, and we decided to drop it for you guys, so you don't need to care about that. For sure, we have more, okay, but here like just 3 very popular we want to introduce for you: the uniform distribution, exponential, and normal. Okay, for our class, we just look at the uniform and normal. Okay, but there are more than that. Okay, and if you want to know more, you need a more advanced class, maybe at least 300 levels. Okay, level 400 level. Okay, and again, say for each distribution, it has like different density curve. Okay, and the error under the curve, again, it will give us the property you care about, right? So for example, here you have 3 different distribution. The first is uniform. For uniform, the curve will be just a line, right? The line. And the error under the curve, it tells you the probability, okay? For example, the second case, for exponential distribution, the density curve, it looks like this, right? It go from high here to low here, right? From high to low here. So which is second plot here. And the last one, which is normal, which is you already familiar with, which is it's a kind of a bell shape, right? It's a bell shape, right? So the error under the uniform, it creates a rectangular shape. The error under the exponential case, it creates kind of half of a mountain, whatever, right? And the normal, the error under the normal curve, it creates a bell shape, right? Bell shape, which is symmetric in the middle, and then has 2 tail, right? 2 flat and a 2 tail. And also you can see that the error under the curve, so for example, if you look at uniform distribution here, right? Probably x from 3 to 6, right? X from 3 to 6 is corresponding to this error. And say if you want to model by the property for the, let me see, where am I? Oh, I think I put here. So from 3 to 6, right? Will be the error under the curve. So if you think that maybe waiting time, right, at the bus station, if you think it's can be modeled by uniform from 2 to 9 or something here, 9, 8.9, right? And if you want to find the property, the waiting time between 3 to 6, right? So it will be the error, shaded error here. And say, if you decide to not using the uniform, right, but you use exponential which is a more accurate way. Okay, when people they model the waiting time in real life, they use exponential. Okay, exponential. We don't learn this distribution in class, but this is the truth. Okay, and the fact people they use in real life. And other times, say say the one probably the waiting time between 2 to 4, right? So which is the area under the curve here. Okay, the software can help you when solution, they have the formula for the curve already, and we can use software to plot the curve. Okay, yeah. And here just for demonstration, I just show you some curve already plotted. Okay, but there's a math behind that. Yeah, same thing, right? So say if you want to model maybe a z-score of a population, right? Maybe weight of ant, right? And something like that. Okay, and you want to find what the probability you get an ant with z-score between 1 and 2, so you get this error. Okay, so now again, your probability is translated to finding the area under the curve. Okay, area under the curve. So let's look at the example and we see it in clearer. Okay. So here, like in physics, right? One important thing people want to do is that they want to model, right? What the living time of the particle, right? And how long it's going to decay, right? So here, like lifetime of particle in minutes, okay? Decay has density function, right? Given below here. So the density curve in this case will be the blue line, okay? The blue line in the plot, okay? Corresponding plot at the bottom here. So the density curve here is this, right? This is the density curve. Right. This is the density curve, okay? Density curve. Okay. Okay. So for sure, you can always check that the total density area under density curve must be 1, okay? To make it satisfy probability definition, okay? So they already give us this plot, but for sure you can always check the total area under the curve will be 1, okay? 1. Total area under the curve, okay? The curve. To make it satisfy probability definition, right? The total probability under the whole sample space must be 1. So which means in this case, to make it a probability is also must satisfy this probability. And actually you can check it, right? If you remember in your 5th grade, I remember I learned it in my 5th grade, right? I'm not sure here what grade you learned, but the area under of the trapezoid, right? If we have a trapezoid, if we have this height, this is the first side, right? The second here. So the total area will be half of A plus B and times the height, right? So for a trapezoid, we call trapezoid. What's the name of this trapezoid? Trapezoid, right? Yeah, I think trapezoid, right? Because diamond different, right? Diamond is a different shape. This trapezoid, right? But anyway, this is the correct formula. Okay, half of A plus B times H. Okay. In this case, you can check that your A is actually 8, right? 8. So half of A and B is 6, right? 6. The top one will be 6. And the H will be 1, 7, right? So you can see it be 1, right? 1. So it's satisfied, right? It's satisfied. But because they only given to us, but here I just want to show that you can always check the error and it must be 1, okay, to make sure it's probability. So now let's work on we have 3 questions, right? What the probability of the particle decay in less than 4 minutes, right? Decay in less than 4 minutes. So which means I will chop it here, okay? So here the figure, I just copy and put the slide here. So we need to find the probability, the particle decay in less than 4 minutes, right? We want to find probability x less than 4, right? Here x is the time the particle decay, right? Here I didn't know x the decay time, right? Decay time. And here we have the PDF the density curve x, okay? So we want to find probability x less than 4 minutes, right? So which means we want to find this area, okay? In this case, you see that to find this error, right? You remember the rectangular formula? What the area for the rectangular, which is A times B, right? If here I don't know B, I didn't know A here, so BG A times B, right? The width times the length, right? So LA is 4, right? And LB is 17, so which is just 4, 7. Okay. So the property, the particle decay in less than 4 minutes, just this error, and you calculate this error, you get 4, 7. Okay. 4, 7. Similarly, right? What the property, the particle decay after 2 minutes and less than 4 minutes, right? So which means you want to find x greater than 2, less than 4, okay? And again, the equal sign does not matter, okay? You can put equal, you cannot put equal, you drop it, it won't affect because we're working with a continuous distribution, okay? You don't need to care about the equal sign. It won't hurt you, okay? Okay. So that time again, if you have the B here, so attention here that the scale on the two axes, it's not the same, right? 1, 7, it looks like much bigger than the other x-axis, right? But anyway, it's still valid thing, okay, to do. So here you have like just a yeah, A in this case will be 2, right? 2. 4 subtract 2 is 2, right? And your B is 17. 2 times 17, which is 27, right? So the property, your particle decay between 2 and 4 minutes will be 2, 7. It's error. Right? And similarly, you can also find the property it decay after 6 minutes, right? Which is you want this error. Okay. Px greater than 6. And if you remember the formula in finding the area of the square rectangle, right? So basically like triangle, right? Triangle. So which is half of H, H here, half of A here, okay? So half of H, yeah, A here in this case will 2, right? 6 to A with 2, and H here would be 17, right? Half of 2 times 17, right? And you get 17, right? Clear? Good. Okay. So now it become to the geometry game, right? 4 grade problem. Okay. So say now let's learn the distribution in a more official way. Okay. Now we look at it more systematic way with formula and plugin, right? So here like the uniform distribution is one important distribution. We learn one other is a normal, okay, in chapter 6. But here like for uniform distribution, some people sometimes they call it rectangular distribution, okay? It's used to model the continuous random variable on A to B, okay, from A to B. If, okay, we'll use that. We have the evidence to show that the outcomes, okay, occurs equally likely, right? Equally likely. So if you think the outcome can happen equally likely, right? And other time you can use the uniform to model, right? So if you believe that, okay, the waiting time at the bus station, maybe from 0 to 20 minutes, and it can be the change for that thing happen equally likely everything, and on the whole interval. So other time you can model by a uniform, okay? And if you use that model, okay, you uniform, and then we denote by U A B, okay? U stands for uniform, and A is low bound of the distribution, and B upper bound, okay? B upper bound. And after you can model that, right? So similar with the spirit of the binomial. After you can model that, and then basically you know everything about the distribution, okay? So the first thing is that like the area under the curve shape, it is a rectangular shape, right? And this is why they put the name rectangular distribution sometimes. The values, it will uniformly distributed between A and B, okay? So it can be anything between A and B, uniformly distributed. No bias here, okay? The width will be 1 over B subtract A, okay? The width is that because from A to B, the length is B subtract A, right? So in order to make sure the total error under the curve is 1, the width must be 1 over b subtract a, okay? This is the width of distribution. So here the width, right, okay? Width, okay? And here I call this a length, right? Length. Okay, length, right? Which is b subtract a, right? So the length will be b subtract a in this case. And the width is 1 over b subtract a, okay? If we have that, we can also find that actually, we can group that the mean and the median will be the same and equal to a plus b divided by 2, okay? And we can also show that, okay, this is not for this class, but you can accept as a fact, okay, the standard deviation by b subtract a squared divided by 12, okay? Accept it, okay? And if you want to really look at the proof, you can go to my office hour, I can do it for you. It should be a big problem here. This is very easy to deal with. You just need some little calculus, okay, to do these things. And the error under the curve, okay, so the probability of yield between C and D, okay. So this case will be the pink error here from C to D. So you can find that basically it's just D subtract C, right? Which is the length here and time the width, right? The width in this case will be 1 over B subtract A, right? And you get the error under the curve, right? From C to D, okay? So this guy is D subtract C, right? And this guy is 1 over B subtract A. So you can find that, right? The property here, right? And also the CDF, okay, which is Fx, okay? So Fx in this case, which is probably yield, distribution less than equal X. And because in this case, you see, you don't have the lower bound, right? But you can only recover the lower boundary by the minimum value A. So you can also plug it and get this, okay? So just accept as a fact, okay? But it can be proved easily by looking at the error before the X value, right? And the last thing is that probably yield between n must be 1, okay? Because it's the range, okay? So total probably under the range, the range must be 1, right? Must be 1 when X belong to the range. So let's look at the example bus waiting time, right? But now we do it more official by using the uniform distribution to model that, okay? So here, like the wait time at the bus station is uniform distributed, okay? On the interval 0 to 20, find the probability that the wait time less than 5 minutes, okay? So at the time, you if you didn't know X is the wait time at the bus station, right? So maybe look at A first and we go B and we go C, okay? One at a time. So A, we want to find the probably the wait time less than 5 minutes, right? And X is the wait time. It is modeled by uniform 0 to 20, right? Okay? This is a notation we use. So find the probability that the wait time less than 5 minutes, right? Which is find probably X less than 5. That time you can plug in the formula here, right? You can also draw the curve and find this error. But maybe if you use the formula, okay, in formula spirit, it's just probably you have like yield less than equal X, right? So it will be X subtract A divided by B subtract A, okay? So in this case, your A will be 0 and your B will be 20, right? In this case, your X will be 5, right? So this thing is nothing else than just F5, okay? And you can use this formula, right? X subtract A by B subtract A, right? X subtract A by B subtract A. So this case will be 5 subtract 0 divided by 20 subtract 0, but basically it's just 20, right? So you get a 0.25. So the probability, the waiting time less than 5 minutes is 0.25 here, okay? For sure, you can also graph it, right? Make the plot and do this strategy, okay? 0, 20. So which means the width is 1 over 20. And you want to find a probability less than 5, right? Less than 5. So which means you use the length is 5. You time the width, right? Is 120. You also get 0.25. So different strategy to do that, right? Some people, they prefer the formula strategy. So you just look at the formula here, right? CDF here. Some people, they prefer using geometry and you look at it, the geometry strategy here, okay? So in B, what the property your waiting time between 1 and 11 minutes, okay? So at that time, it come back to if you are a formula type person, you just use the formula, right? 1 to 11. So D subtract C, right? So in this case, your D is 11 and your C is 1, right? D and C, okay? And you just plug in D subtract C divided by B subtract A, and you get 0.5, okay? So probably your waiting time between 1 and 11 minutes is 0.5, right? And again, if you are geometry type person, you can also look at 1 to 11 to find the error, okay? The difference, right? So last one, okay? Find the 70 percentile value of waiting time, right? 75 probably waiting time. So this is a very typical problem, right? We did see a lot in chapter 2 by the 70 percentile value. So here, let me insert this slide. Okay. New slide here, right? So basically, we want to find a K, right? Such that X 0.7, right? 70 percentile value. This is the definition of 70 percentile value, right? So 70% observation less than this value and 30% bigger than this value. Okay, this is 70 percentile value. So in this case, if you look at the formula we provided here, right? It's just a CDF formula here. So it will be like K subtract A, in this case 0, by 20 subtract 0, right? So which is K by 20, right? And we have this equal this, right? So which means your K is 20 times 0.7, and you make 14, right? So the 70 percentile value of the waiting time will be 14, right? 14 minutes. So among 100 observations, 70 of them will have the waiting time then 14 minutes. 40 minutes, and 30 of them will have the waiting time bigger than, right? 40 minutes, okay? So let's look at the quiz here, which is the quiz for the pub quiz for class today, okay? First is fixing, okay? I will open the quiz today, and you have the time till tonight to finish, okay? If you want the bonus, okay? And if you don't want the bonus, then just feel free to skip, right? So here, like the seamless thing, right? Time a technician needs to fix a furnace at AC heating and air conditioning service is modeled by a uniform from 5 hours to 4 hours, okay? So in this case, your A 1.5 and your B 4, right? So it's your A, your B, okay? So now the first question is that I find the property that a randomly selected furnace repair require more than 2 hours, okay? So basically in this case, you need to find the property X greater than 2, right? Yeah. So you have to be smart, right? Because if you want to use the formula, in this case, you don't have that formula. Very straightforward here, right? So you can turn around a little bit, right? This way, so either you can use geometry. Okay, so I'll show you two strategies to do it, okay? So one strategy, using geometry, the fixing time from 1.5 to 4 hours, okay? So which means the width here, which is 1 over 4 subtract 1.5, okay? This is the width. And you find the property, your fixing time is greater than 2 hours, right? 2 hours. So you do this area you want to find, right? So you know the width, which is in this much, right? This is the width. And you have the length, which is this much, right? So you can find the error here. But another way to do that, by using the formula, by doing a little bit smart, right? So X greater than 2, which is 1 subtract X less than equal 2, right? Right? And then you can get back to this, right? X less than equal 2, right? So just, so in this case, you just have, know that, right? Know that probably X less than equal 2, just a CDF, right? And basically it's equal to 2 subtract 1.5 divided by 4 subtract 1.5, right? Okay. So similarly, find the property, the wait repair time less than 3 hours, right? So this case is straightforward, right? It's less than 3. So basically it's just 3 subtract 1.5 divide by 4, subtract 1.5. It's very straightforward by using the formula here, right? You see the formula here. And last one, find the 30 percentile value of the furnace repair time, right? So again, we know K is the 30 percentile, right? 30 percentile value. And we have Px less than equal K equal 0.3, right? And know that we have to know that Px less than equal K. The equal sign does not matter, okay? So sometimes I drop the equal sign, okay, to make it fast. But this is something you have to pay attention here, okay? K subtract 1.5, right? Divide by 4, subtract 1.5, okay? So by blocking that, right, you can solve the K, right? So to find K, right? Find K. So this is the quiz for the class today, okay? So, okay, I think we finished the lecture on time. Okay, see you next time.